I'm recording. So if you have any questions, ask them loud. All right. Unit 2, one-dimensional kinematics. Now that pink worksheet we just did, it had little dots on it, right? Those dots were in a straight line. What are those dots? What were those dots called? What do they call them on the paper?
Ticker marks.
Call them ticker marks or a ticker tape diagram, right? Right? Now it's kind of an old term. Your book uses a description for it called a motion diagram. A motion diagram. Now, ticker tape diagrams, motion diagrams, you can also think of them as called a strobe diagram. Why do you think we call it a strobe diagram?
Dots.
Has anyone ever played around with a strobe light before? Okay. The strobe light flips on and off real quick, right? So if I were to throw something when a strobe light's going, right, you would see that object at different points along its path. Would you see the whole path? No, if it was completely dark in here and I threw a baseball at Jameer, okay, he would see the baseball here, right? Then he'd probably see the baseball here, right? Then he'd see the baseball here, and then we'd hear him get hit before he saw it again, right? That's how a strobe light works, okay? It blinks at a certain rate so that you see the location of the object at points along the path, okay? Motion diagrams are a lot like watching something move with a strobe light. That's why they're also called strobe diagrams. They're also called ticker tape diagrams. Okay, they're also called particle diagrams, and we'll show you all of them in a second. All right. A motion diagram is a series of images showing the position of a moving object at equal time intervals. Right? So it's a series of images showing the location of an object at equal time intervals. Okay, so I'm going to draw a motion diagram for a car going down division at 25 miles an hour. Yep, one-dimensional.
Should we draw this?
Completely up to you.
This bar is so nice looking.
I don't know. I ask myself that every morning. Man, I should have taught how good I can draw things. Now I draw y'all a picture right here.
It looks like a top hat.
It does look like a top hat with wheels. It's like a Monopoly car. All right, so here's my car, right? Now, how far is the car apart each time? Is it the same distance or different distance?
I think I tried to make it the same.
Okay, the intention was to make it the same, right? So this car has a constant velocity, right? Now, is this 3 cars or 1 car?
1 car.
It's 1 car. It's 1 car shown at 3 different times, right? So this could be time equals 0.
So I'm actually press the back end on the last one.
This could be time equals 4 seconds, okay. If this is 4 seconds, what's this?
8.
8 seconds. And that means our time interval is what?
4 seconds.
4 seconds. Okay? Because the time interval is the space between pictures, the time between pictures. So for this one, our time interval equals 4 seconds. Okay? And that's a motion diagram. Does that make sense? Now we can make an emotion diagram by putting smiley faces on those cars.
Will you ever ask us to draw it at like 12 seconds?
We could. Okay. I could say, where's the car going to be 12 at time equals 12? Right? Be the same distance away, assuming velocity is still constant. Good question. Now, for those of you that are not artists like myself, you would much prefer the particle model. Because when you use the particle model, instead of drawing the whole car, you pick one spot on the car and represent it with a dot. Okay? So in the particle model, use a single particle in the object to represent the object. So it's a motion diagram using a dot instead of an image. Okay? So for example, I could take this one and I could pick a spot on the car. All right, someone pick a spot on the car. Doesn't matter where.
The middle.
The middle of the car.
Yep.
Okay. So instead of drawing the car, I could just draw those dots.
Did you forget an N?
No, it's there's two little squiggles there.
Where?
Here. Here's the first bump.
I'm not talking about right there. He's referring to.
It's
talking about motion.
Motion. No, it's right there. You guys didn't see it? It's right there. Hey, gentlemen. Thank you. He's just jealous. Completely jealous, Reggie. So, instead of using the cars, you can use dots. Now, for obvious reasons, I use the particle model. Okay? Especially when we're talking about cheetahs or giraffes. Okay? I gotta use the particle model. Alright? Alright. Any questions about motion diagram versus particle model? Okay.
Same thing.
They are the same thing. Now, these are also known as,
Why is there verses
Okay.
there then?
also known as strobe photos, okay, or strobe diagrams, or ticker tape diagrams. Okay. So I don't know what physics book your college physics teacher is going to use, but they might use ticker tape. They might use strobe. Well, I don't know why you wouldn't take college physics. Okay. The best career path there is.
You're crazy.
All right. Are there any questions about that? Any questions?
I have a question.
What's that?
Would you ever be a college physics teacher or professor?
I have actually after next spring I'll have a master's degree in teaching physics.
Are you gonna go further?
So then I actually am trained enough to teach physics. I can teach physics right now. But what? No, I can't teach right now. I can. I'm able. We don't have students on thing.
Well, next year there will be.
There's just one. Right. So
I'll take it.
so I can teach. Once I get that master's degree, then I'd be qualified enough to teach physics classes at Grand Valley or CC or any university that has professors that are allowed to teach and not be tenure track professors.
I thought it was 8 to 10.
No, tenure track. That means you're a tenure track professor. That means you're trying to become you have a doctorate and you're trying to work there and do research. But if you're just like a professor or a teaching professor, then that means you just have a master's degree in the field and you're just there to teach. You're not there doing research.
So you might do that?
Yeah.
You don't want to do that at all.
No, the staff is much more stable than
That's
that.
what you look at.
You wouldn't want to
See,
Can't you do both, like on weeknights?
I could, but then I never see my kids.
Good? I know you want kids.
I've actually thought about doing that in the summertime, like for any summer classes, but I actually think the summer school here probably pays better. So I might as well just keep going for summer school.
You did summer school here?
Yeah.
You should push for the.
What you did for? Yeah, you would know.
I haven't really.
What'd you do this year?
You guys sign up, you can. All right. So you guys have a picture that looks a lot like this. Okay? Guys, listen up, please. Omar, Kyle. It says create a motion diagram, strobe, or ticker tape for an object traveling at the speed shown. Each tick mark on an axis is 1 meter. Use, that's an A, not a D, use a time interval of 1 second. Okay, so, I'm going to do the first one for you. Here's time equals 0. Here's where I'm starting, right? Right? So if I'm going to draw my particle model for this object, where's my next dot go? Okay. Since the time interval is 1 second, I'm making a dot for every second of motion, right?
Yep.
If this one travels 1 meter per second, that means I need to put a dot
At everyone?
at every meter. Okay? Because each dot is 1 second. So 1 second later, it'll be right here. 1 second later, right here. 1 second later. 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 1 second later, and last one. Okay?
1 second later.
So those will be our dots. Does that make sense? Okay. I'd like you guys to make motion diagrams for the other two objects. 2 meters per second and 4 meters per second. Now the time interval is still 1 second. Guys, please focus on the.
Oh, yeah, it's a cool.
Don't do it on the next part yet. You can those there a lot.
Come on, Bob.
Alright. Any volunteers to draw theirs on the board?
Me.
Which one, Kyle?
I want the second one.
I'll do the third one.
Okay. Thank you, gentlemen.
I gotta roll it.
Now, gentlemen, you are about to be on YouTube, so keep that in mind.
Okay.
Behave appropriately there, Kyle. And Skylar.
So, what do I do now?
You won't, but.
Step up here.
They will.
Oh, wait.
Shouldn't be Coach K Waffles.
Something like that. Right there.
Nice job, gentlemen. Alright, so how'd they do? How'd they do? No, it's easy to catch. It's a marker. Jameer, are they correct? Reggie, okay, are they correct?
Yeah.
Yeah. All right, good. Any questions about the motion diagrams? Any questions? Okay. Next thing we're going to talk about is something called a position vector. Thank you, Skyline, a lot for moving your feet. Okay. A position vector. All right, we'll come back to this in a second. So I might try right there. All right. Now, do you remember what a vector is?
You weirdo.
What's a vector? Has both
Magnitude and direction.
magnitude and direction. Okay? Now, a position vector depends on our coordinate system. I guess I don't want to turn that off yet. Okay. Depends on our coordinate system. So here we have a coordinate system, don't we?
Mm-hmm.
Okay, on this line right here, this represents an axis or coordinate system. Where's the 0? On the left, right? All the zeros on the left, right? Which way is the positive direction?
To the right.
That way.
To the right. All right, when you define a coordinate system, you're defining a positive direction. Okay? Your coordinate system is a lot like your reference frame. You guys remember that word from last year? Okay? That term reference frame? A reference frame is a way of looking at a situation. Right now, our reference frame is that the left tick mark is 0, all the way to the right tick mark is 10, each tick mark is 1 meter. Right? That's our reference frame. I picked that for you. Could you guys just as easily have picked your own? Right? You could have said 0 was on the right. Okay? And the positive is going left. You could have done that. You could have put the 0 on the right and said positive still to the right and had these be negative on the left side. That's okay. That works too. Alright? Your reference frame is how you look at the world. Right now, you guys are all sharing a reference frame. The reason why you're all sharing a reference frame is because we're moving at the same velocity in the same direction. Some of you say, wait, I'm not moving right now. But you are. We're all on planet Earth, which is doing what? Rotating and moving in an orbit. Right? So not only are you all rotating together, but you're all moving with a velocity around the sun together. And because we are all moving together in the same direction, we share the same reference frame. Okay? Now once I start walking towards you, I am no longer sharing a reference frame with you guys. Okay? In your reference frame, I'm walking towards the back of the room, right? Right? In my reference frame, you guys are all moving towards me. As I walk this way, you're all moving towards me. Okay? Now I know that I'm walking, and that is why you're moving towards me. But in my reference frame, you guys are the ones moving, not me. You guys remember that? Does that make sense? Yeah. Okay. So it is your choice to define your reference frame however you like. Okay? You can define it like I did right here. You can define it in another way. All right? It is very important on tests, especially when we're doing something like this, that you tell me where your 0 is at and you tell me which way is the positive direction. If you don't, I'm going to assume the 0 is all the way to the left and the positive direction is to the right. Like I have on the board. Does that make sense, guys? Does the whole reference frame thing make sense? Yeah. So, where's my origin here? On the left or on the right? On the left. Perfect. So when we start talking about position vectors, that's why we need to talk about reference frames real quick. Because a position vector is a vector that points from the origin to where?
To the next step.
Points from the origin to the
Positive direction or
to the object. Okay? A position vector is a vector that points from the origin to the object. So it's a vector that points from the origin to the object. Okay. Now vectors have two quantities. What are they, Jose?
I just had it.
You know what it is.
I know. Oh, direction.
Direction and magnitude, right? So a vector has two things, direction and magnitude. Direction is which way it points. What's magnitude? What's magnitude? The length. Okay? The length of the vector is the magnitude. Okay? Now, if I'm figuring out how far an object is from its origin, if you look at that first one, that first picture right there, okay? How far is that first dot from the origin? What do you think? That first picture, how far is that first dot from the origin?
Not that far.
Not that far. How long is it?
1 meter.
1 meter. Right? 1 meter is the D word. The distance. Okay? The distance is the length or the magnitude of the position vector. Because the distance is how far something is away, right? Right? How far something is away, that's the distance. Okay, does that make sense? Yeah. And because distance is the magnitude of position vector, a position vector is denoted by a letter D. Okay? So D denotes position vector.
Hey, you know when we're gonna start writing 30?
I do not. All right, so if I'm going to draw a position vector for this first one, okay, I'm going to draw it right down here. It says now go back and draw position vectors above each axis for the first second of motion. Okay, so my position vector for the first second of motion is going to start here and end where?
First dot.
There's my position vector for the first second of motion. Does that make sense? And since this is the first second of motion, I will call this D sub 1. Does that make sense? Can you guys draw the next two? Okay, so what does this one look like?
You know what it looks like.
I do know what it looks like, but I'm asking you.
I know what it looks like.
Where does it go?
It goes all the way over there
To what?
to the second one.
So it starts here and goes to the...
Keep going. Go. Stop.
Okay.
This is first.
So that'll be D1 for the second object. Right? How does the position vector for the last one compare to the first two?
It's way bigger.
Way bigger, right? Starts here and goes...
Stop.
Okay. So that'll be D1 for the second object. Does that make sense, guys? Okay. Now the next thing we need to discuss is something called displacement. Now displacement and distance are often misunderstood. They're often confused between one another. When I say the displacement of the object, what am I talking about? How far it is from the origin? Okay, that's close. Okay. For this one, that works because we start at the origin. Let me ask you a question. Let's say I go for a walk every morning. I start on my porch. I walk 3 miles. I come back and end on my porch. Right? What's my displacement?
0.
0. You guys all remember that test question from physical science, huh?
Yep.
My displacement is 0. Why is my displacement 0? I ended at the same spot that I started. Right? So my displacement is how far I am from where I started. Okay? I can take that how far I am from where I started and sum it up with 2 words. Actually 3. You know what the 3 words are?
No.
First one is change. Second one is the smallest one.
And
In
Direction.
what's the third one?
No.
Not direction.
Change the speed.
location. Direction.
Displacement.
A word. A word. Nice job, Kevin. Change in position. Your displacement is your change in position.
Position.
Okay? Now what symbol does displacement get? Delta D. Okay? That triangle is a Greek letter. It's called delta. What does delta mean?
3.
Part of a sorority. Gotta have another letter, not just one. Usually 2 or 3. Okay, what does that delta mean?
3.
What does the D mean?
Distance.
Vector.
D. Distance vector.
Distance vector. Position, right?
Position
The
vector.
D means position, doesn't it?
Mhm.
So the delta means change. Okay? The Greek letter delta equals change. So this symbol right here is telling you the definition of displacement. Okay? It's the change in position. So that leads us to an equation. How do I find the change from one spot to another? How do I find the change? Is this an addition problem or a subtraction problem? Subtraction. So that means that delta D, or displacement, equals no. What do you think? What do I do with the? What do I do? I need. How many positions will I need? 2. What do I do with the 2 positions? Subtract them. Okay. It equals our final position minus our initial position. And that is our displacement. And that is our first equation for this unit, which I have conveniently written over there. Okay. All right, all the equations we'll use on the board. Right over here, Jameer. It's in blue. Okay, my delta's kind of funny looking. All right. All right. So does that make sense for displacement? Okay. Now is displacement a vector? Guys, is displacement a vector?
Yeah.
Yes, displacement is a vector. Now, how do I find the displacement vector, Reggie? What do you think? I use a cool little process that you guys learned last unit. I gotta take 2 vectors and do what with them? I gotta add them. What's it called, Monty? Tip to tail method. And now it's called vector addition. Right? Vector addition. Put parentheses the tip to tail method, right? Right? You guys remember doing that last unit? Okay. So back to our example.
This class is long.
Right? Only 60 minutes, Kyle.
It doesn't feel like it.
Time flies when you're having fun. It always ends up being shorter than I thought.
When I have.
Alright, I am. Alright, so next one. So we have one position vector. Can I find displacement one position vector? No, what do I need now? I need 2. I need a second one, right? So I want you to draw a position vector for the second of motion. Okay? So if it's a position vector, that means it starts where? Origin and goes to the second dot. Now, I want you to draw it using, or on the bottom, sorry. You guys have different colors. Okay? So that would be my...
What if we already drew it above the other line?
Well, then you didn't follow direction because it says on your paper to drop below. Yep, so you don't get confused.
Oh, okay.
So, those are my 2 position vectors, right? Right? Okay, I want you to draw the second position vector for the other 2 as well.
So wait, what did you do?
What?
I don't know why you did that.
You don't know why I did that? Okay, that's the second position vector.
So you just go up one more?
Right, because the second dot is right here.
That's okay. That's what I'm going to do.
We have to start from
I'm just going to go up.
You have to start from the beginning. Because position vectors go from the origin to the
The next one.
object. So the next one starts here. Where does it go?
All the way out there.
Okay, good. The next one starts here. Where does it go? Right? This is D2. D2. Okay. So, there I have all my position vectors, the first and second, right? So now how can I find displacement?
You got to minus the final one.
We got to subtract the second one, or the first one from the second one, right?
Wait.
So vector addition, am I allowed to move the vectors around? Okay. I can move them, I just can't change their what? I can't change the magnitude, right? So if I want to figure out the displacement right here, I can take this vector, and since it's subtracting, what do I do with it? You flip it, right? But I gotta keep the magnitude the same, don't I? Tip to tail, so I take the tail of this one, put it at the tip of the other one, right?
Mhm.
That's D1 now, isn't it? So what's my displacement?
2. Wait. 1.
1 meter, right? 1 meter. So here, you guys will probably dash it, so I'll dash on mine. That is my displacement for the first one. Okay? I'll make a little key for you. Delta D is going to be dashed in blue. Okay? So now for the next one. What am I going to do with this vector? I need to move it and flip it. If I take this vector, I move it down here and I flip it. So it looks like this now. Right? Tip to tail. Right? How long is my displacement vector? There's delta D for this one. Does that make sense? Guys, does that make sense?
Yeah.
Now, since the displacement vector is 1 here, does this mean that this point after 2 seconds is 1 meter away from the origin? Is that what it means? No. It just means that how far it went between 1 second and 2 seconds was 1 meter. Okay? Displacement vectors are not position vectors. They don't tell us where it is relative to the origin. They just tell us how far it went between the 2 times. Okay, does that make sense? You guys find the last one? Alright, did the last one?
Yep.
How long is the last one then, Kyle?
It's really long.
No, it's not.
It's like 4.
It is 4. Good. Okay. So for that last one, we take this vector, we flip it, move it down here. Oh, it's too long. Come on, go back. Hurry up, go back. There's the mountains of Colorado. Oh, man.
Aha!
All right, have a good day, everybody.
Mr. Brent, we gotta talk about something.
What's that?
God, why solar?
Oh God, oh God.
Oh, here's the displacement vector in case you're wondering.